So this is a video that I've wanted to make for quite some time on how some of the practical aspects of magnetics work. I wanted to make this video because this is a topic that I don't think is taught well in university, and there also aren't a ton of great resources available on the web. I've had to learn all this stuff myself, and this is the guide that I wish I had when I got started. So if you're an engineer trying to use magnets in a design, or a student trying to learn a bit more, if you're used to seeing diagrams like this that just don't make much sense, hopefully this video will clarify a bunch of things for you. I hope you enjoy, and if you notice any mistakes I've made, please leave a comment correcting me. So to jump right in, one of the really handy things about magnets is that they actually share a ton in common with electric circuits. And this is nice because electric circuits are pretty well taught for the most part. So if we were to consider the most basic electric circuit here, we've got a voltage source, like a battery for example, a current flowing through the circuit, and some sort of resistance in the system, maybe like a light bulb. Now, magnetics are very similar, but how does this compare? So, in a magnetic circuit, the magnet acts like a voltage source. Technically, it's equivalent to a current source, but it's a lot easier to think of as a voltage source. And if we were to draw the current in the circuit, we'd draw it like this, with parallel lines of current flowing from the North Pole to the South Pole. So we've got these lines of current flowing from the North Pole to the South Pole, but the question is, what is the resistance in this system? What is the equivalent of this light bulb? Well, in this case, the answer is actually the air. The resistance is created by whatever material the field happens to be flowing through. However, there is one major difference with magnetics we need to consider. If we were to zoom inside this wire here, we'd find that there's some sort of current density going through the wire. And if you were to integrate this, for example, we'd get the total current. The key though is that we don't really care about this current density, just the total amount. So you might say there's 10 amps flowing through this resistor here, but you don't really care how it's doing it for the most part, just that it's there. For magnetic circuits, we do care about current density, and this is where you commonly see heat maps like this to show how the current is actually distributed in the circuit. For magnetics, we call this flux density, and it's also commonly referred to as the B field. This is also what the units of Tesla depict. So the key here is that we do have this current flowing from north to south, but it's different in different places, and we care about those differences. Whereas for electrics, we just care about the total amount of current in the circuit. So just to kind of summarize everything here, we've got our electric circuit and our magnetic circuit. Now, these are some of the equivalent terms and variables you'll see for each type. So the equivalent of voltage is magnetomotive force, the equivalent of current is flux, but we're currently working in units of flux density, so similar to current density. And then finally, the equivalent of resistance is reluctance. So we basically have magnetomotive force created by the magnet, flux flowing through the circuit, and then reluctance due to the air interacting with the magnetic field. Now, there is one more parameter we need to talk about. Permeability is similar to electrical conductivity and represents how happily a magnetic field will flow through a specific material. It's inversely proportional to reluctance, but reluctance depends on geometry, where permeability is material specific. When it comes to permeability, materials fall into basically two categories. Ferrous materials have high permeability and magnetic fields will happily flow through them. This is basically your steel, iron, electric steel, and certain grades of stainless. Most other materials have low permeability and therefore create high resistance in the magnetic circuit. This is materials like air, aluminum, plastic, and interestingly enough, even magnets have a low permeability despite acting as a circuit's voltage source. Here's a table of permeabilities from Wikipedia. Everything is in relative permeability, so just compared to a perfect vacuum. One of the things to note is that basically everything at the bottom has a value of 1. This is all your non-ferrous materials, and what this means is that materials like wood, aluminum, copper, and water are all basically the same as air from a magnetic perspective. Up at the top, we can see how steel has about 100 times higher permeability than these non-ferrous materials. Some of these other materials are much higher, but for the most part, these are just super alloys that you'd never actually work with. So given what we know at this point, this magnetic field here is flowing through air, which means that the circuit has a high resistance because air has a low permeability. Now, I want to ask a question. What happens if I were to take a piece of steel and stick it onto the end of this magnet? Well, we know that steel has a high permeability, which means that the magnetic field should like to flow through it preferentially. And if we look at the results here, that's exactly what's happened. The magnetic field flows through the steel wherever possible. Keep in mind the field still has to travel from north to south, but it really likes to flow through the steel wherever possible because the permeability is so much higher. Now, this leads us to a key point. Magnets always want to do whatever creates the lowest possible circuit reluctance. Going back to our previous example, this tells us that if we put a block of steel near this magnet, there's going to be a force pulling the block towards the magnet because the circuit reluctance is lowest when the block is touching against it. Here's the formula for reluctance, and this tells us all the things that we can do to decrease it. So we can decrease the length of the circuit, we can increase the cross-sectional area of the circuit, or switch parts of the circuit to materials with higher permeability, which is what we've done in this example. So magnets will always create forces to do any of these things in this equation. So this is all pretty straightforward, but there's one more interesting phenomenon we have to talk about. Looking back at the previous example, what happens if we make this piece of steel very thin? Well, first of all, we see that the flux density is increased. And this makes sense because the field wants to flow through the steel, but we've decreased its cross-section, so the density has to increase. However, notice how some of the flux is also leaking through the steel into the air. This doesn't really make sense. This leads us to a concept called the BH curve. This is essentially a plot of the material's permeability at different flux densities. We can see here that at low flux density, the steel will have a high permeability and readily accept more flux. However, there's a key point where the steel doesn't want to accept any more flux. Its permeability starts to drop off. This point in the curve is known as saturation. So this is what's happening in the example below. The flux density in this area has gotten so high that the steel is saturated. Its permeability is decreased to the point where some of the field actually prefers to flow through the air now instead of the steel. This is a big departure from electronics. It's not like current in an electric circuit will just leave the wire and start going through the air at some point. The key difference is that electrical resistance is constant, but for ferrous materials in a magnetic circuit, this parameter depends on how much flux is flowing through the material. So at this point, we've looked at most of the key concepts, but what now? How do we actually use this knowledge for designing stuff? I'm planning to make a few more videos explaining this in detail, but if you want to get started, here's a couple things you should look at. The first is magnetic circuit calculations, which can be done by hand, and they're pretty accurate for a lot of simple cases. So let's consider a basic magnetic system like this. We could represent it with an equivalent electric system drawn like this, where the resistance is due to the air gaps because steel has pretty low resistance for the most part. This calculation process uses essentially electric circuit formulas to calculate the current or flux going through the system. Once we know the circuit flux, we can look at the total amount of flux in the air gaps to calculate the lifting force on the bottom beam here. This is actually very simple. All the calculations are just slightly modified from what you'd do for a normal electric circuit, given some of the principles that we've already talked about. However, magnetic calculations break down once you move away from simple cases. For example, if we were trying to calculate the flux for this system here, we need to find the air's resistance. The problem, though, is that resistance is proportional to cross-sectional area and length traveled through the material. So, what length do we use? This one? This one? Do we use an average of the two? The same goes for cross-sectional area. For many magnetic problems, you have no choice but to switch to FEA programs to calculate these parameters. One of the best free ones is called FEMM. It's limited to 2D, but you can approximate a ton of systems quite accurately with this tool. I'm definitely going to make a tutorial or two on FEMM in the future. Lastly, start playing around with magnets and try to get a better feel for how these concepts work. Why do the magnets stack nicely together? Can you picture the circuit in your head? What happens when you stick them onto a thin piece of steel or a thick one? If you stick them onto a piece of steel, is the surface still magnetic after? The more you can play around with these things, the more it'll help to better cement some of the concepts in this video. So that's all for this video. I hope you've learned something and have enough to get you started in the right direction. I'm planning to make more videos on magnetics in the future, and I'll add links to them on this screen once they're released. In the meantime, please leave a comment if you have any questions or thoughts, and try not to pinch your hands when you're inevitably playing around with neodymium magnets after watching this.